Hello. Oh, just a second. Let's just. That's not really any better. Anyway, hello to those watching this in the future. I've already said hello to people who are here now. This is semester 2 in 2022, and this is a revision seminar for Maths 1B. And there's been some requests, and I will, well, we'll see what we can get to. Okay. Okay. So this was written on the board. Before I say anything, I would like you to, it's good practice to think for a moment what you think about this before I say anything. So while I'm thinking of what I'm going to say, I'm going to let you think for 30 seconds or so about what's going on in this and how you feel about it. All right. So I'm going to start with just a straight up, what do these words mean? Orthogonal means right angle. So ortho means correct. An orthodontist is a person who makes your teeth correct. For example, don means teeth. And gon means angle, as in hexagon has 6 angles. So it literally means correct angle, so right angle. Isn't that nice? So it literally means right angled. Things are orthogonal when they are at right angles. Mathematicians extend the meaning of that to things that don't have angles because we're fun like that. But for vectors, it really does mean at right angles. Okay. Orthonormal is a portmanteau, which is a word that has made by joining 2 words together, and we're joining together the words orthogonal and normal. And in this context, normal means length 1. But when mathematicians say normal, they mean any number of things. They could mean anything by normal, so I'm sorry. There's sometimes when they say normal, they mean at right angles. And sometimes when they say normal, they mean following the Gaussian distribution. And sometimes when they say normal, they mean length 1, which is what they mean today. So what that means is right angles and length 1. When we're talking about vectors, anyway. Sweet, doing well. Cool. I'm going to add one thing to this thing. To tell if things are at right angles, then you know that the dot product is 0. So that's how to know if things are at right angles, the dot product being 0. Anything that you can define a dot product for, we declare that dot product being 0 means at right angles. Because we think that's nice, mathematicians, I say that now because if you're planning to do differential equations in second year, this will come up not for vectors. So just know now, it will come up again. Almost everything in Maths 1B is there because at least one person studying Maths 1B will need it in a future course. All right. And basis, well, that's a specialized terminology. So let's remind us what basis means. A basis is a piece of information about a subspace. So it's sort of like a basis isn't a thing all by itself. Like, nothing is just a basis. Things are always a basis for something. And what you're a basis for is a subspace, or the whole of R, whatever R you're in, R4, R3, or R2. So it's information about a subspace, and the basis belongs to the subspace. And a subspace has lots of different bases. Yes, that's the correct plural. And some of them are orthogonal and some of them are orthonormal. And some of them are neither. So a basis is a way of describing how to get to every point in the subspace. And so the official definition is that a set of vectors is a basis for subspace W when, and two things have to be true for it to be a basis. First, they have to span W. And second, they have to be linearly independent. And what they mean by span, see, we've got a definition for basis which use another technical terminology, so we'll get to the bottom at some point. What we mean by span is that everything in W can be written as a linear combination of these things. So if W is something that's in big W, then W is something times V1 plus all the way up to something times VK. That's what span means. In this context, it's the verb span. And linearly independent means that none of them is a linear combination of any of the others. But the definition of linearly independent is A1 V1 plus AK VK equals 0 only when A1 is 0 all the way up to AK is 0. And that's called the trivial solution to this equation. So both span and linearly independent are both about linear combinations, things with constants times the vectors. But linearly independent is about there only being one way to make the zero vector, and or alternatively, each of them is not a linear combination of the others. And span is about making all of these other things using your linear combinations. So that's the definition of basis. I'm going to stop for a second and allow people to think about what I've said and ask a question if they've got one. Cool. I'm going to do that every so often. I'm just going to stop and let you think and or ask questions. Okay. So what that means is, if you've got an orthogonal or orthonormal basis, it has to be a basis first, and then it has to be orthogonal or orthonormal. It is worth noting that if vectors are orthogonal, then they're automatically independent. So if you know they're orthogonal, then you can be guaranteed they're independent anyway, and so you don't have to check the independent bit. So in fact, this is a classic proof that usually appears in one of the tutes or assignments or exams to prove that if vectors are orthogonal, then they're independent. Would you like me to show this proof? Okay. So while I'm here doing a proof, I might as well talk about proofs. Proofs are, since the days of Euclid in ancient Greece, proofs have been the standard for mathematics. Though other cultures have different standards for mathematics, and that's okay. But here we are, this is where we live. And since Bourbaki in the 1940s, proofs have been like the standard. They were really big on this, the Bourbaki team. And they're the people who basically removed all pictures from mathematics, which is really sad, and we should put them back. Anyway, sorry. I'm in a weird mood this morning, so just interrupt me if I'm going off track. So vectors are orthogonal. If vectors are orthogonal, then they have to be independent. So this is an if-then statement. And an if-then statement in a proof usually looks like suppose blah, 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 therefore. So we're going to say suppose V1 up to Vk are orthogonal. And we'll do some working, and I'm going to make it fit in this space. I think I've got enough space. And at the bottom of here, we're going to say, therefore, V1 up to Vk are linearly independent. So my advice for doing proofs, especially in exams, is to turn your if-then into a suppose therefore, and write one at the top and one at the bottom so you know where you've been and where you're going. So on the Maths Learning Centre wall, there's a big problem-solving chart, and one of the things on the chart is to know what the goal is. And today our goal is to prove linearly independent. And at any point in a proof where you don't know what to do, the best thing to ask yourself first is to pick something you've written or pick something that's already written on the page and ask yourself, what does that mean? And write it down. So, what does it mean for them to be orthogonal? Someone say. Yep. Yeah, I heard someone mutter right angles, which is also true. So well done. So they're right angles, which means their dot product has to be 0. So to be orthogonal, that means that every one of them is orthogonal to every other one. That's implied in the way it's said. And so that means that Vi dot Vj is equal to 0 when I is not equal to j. This is how a mathematician would normally say it. Because they want to cover the statement that the dot product of any two of them is 0 in sort of notation sort of way. And so the I and the j is standing in for numbers from 1 to k, and the dot product won't be 0. Yeah. Oh, okay, just a second. I have to add something. If non-zero vectors are orthogonal, then they're guaranteed to be independent. Because any list of vectors that has the 0 vector in it is dependent. And so that wouldn't work. All right. So suppose they're orthogonal and not 0. Okay. So they wouldn't be independent if any of them was 0. Okay. And I had to put the I not equal to j, because if Vi dot Vi would be the square of the length of Vi, and that's not 0 if it's not the 0 vector. Sweet. So here's a question. What does it mean for them to be linearly independent? Oh, I've got a chat. Sorry. The chat went away. Yep. I'm going to answer that question in the chat in a moment. How do you tell if things are linearly independent? I ask you this because it's important to know this. Okay, so you've said they're not linear combinations of each other. That is the truth. If none of them is a linear combination of any of the other ones, then they're linearly independent. But that's really hard to do in a proof. The definition we've chosen for linearly independent about the equation and the trivial solutions is chosen specially because it's the easiest one to do in a proof. Okay, So in order to prove they're linearly independent, I have to make an equation like this and show that the only solutions is that their coefficients are all 0. So, oh crap. That was bad. Suppose A1, V1 up to AK, VK is 0 for some A1 up to AK in R. So to show things are linearly independent is an if-then statement of its own. If this, then that happens. I've written it as only when, but it's actually, if, then. So that's an if-then statement of its own, so I'm going to do a new suppose therefore. So at the end of this bit, I want to say therefore A1 is 0 all the way up to AK is 0. And if I can show working in between that gets from here to here, then they're linearly independent. Because that's what the definition of linearly independent is, that if you start here, you get here. So now I have to somehow get from here to here, and I have to use the fact that they're orthogonal, or I wouldn't need this proof. So somehow I have to use this fact that the dot product of any two of them is 0. What am I going to do? I've got an idea, but I want to know if someone else has an idea.
You dot both sides by one of the vectors.
Okay, so I'm just going to repeat that. You dot both sides by one of the vectors. Well, that would definitely introduce a dot product into my equation, and then I can use this. Okay, so let's say do dot product of both parts with VI. So we've got VI, damn it, I'm not going to have enough space. It's worth a try. All right, I'm going to dot all of these with VI. So I'm going to do the full working just to make sure I'm absolutely sure I know what I'm doing. I can squeeze it in. Okay. Dot product expands out over addition, same as ordinary multiplication, and constants can come out when I do dot product as well. So that's going to be A1 VI dot V1, and somewhere in the middle there's an AI VI dot VI, and at the end there's an AK VI dot VK, and VI dot 0 is 0. Yeah, I really do need to move that down. I know where I'm headed. Okay. It's almost never a bad plan to expand things out if you don't know what else to do. Unless it's the denominator of a fraction, that's almost never a good idea. But if you don't know what to do, expanding things out is not a bad plan. So here's the thing, I know that AI.V1 is 0. I mean, if I isn't 1. And all these dot products, they're all 0 except this one. So since vi.vj is 0 for I not equal to j, what we get is ai.vi equals 0. You might not have noticed something quite trivial that happened here. This, not trivial at all actually. This 0 was underlined because it was a vector. This 0 is not underlined, it's a number. Because when you do the dot product two vectors, you get a number as the answer. Now I know that vi isn't the 0 vector, so that means that vi.vi can't be 0. So the only way to dot a vector with itself and get 0 as the answer is to have the 0 vector to begin with. And so since that's not 0, and these two numbers multiplied together produce 0, that must be 0. So this argument works no matter what I is, and so therefore all of them are equal to 0. And therefore the vectors are linearly independent. Just enough room to fit it all on the screen. How are people feeling about that? At least one thumbs up, so we're doing okay. But if you don't feel that way, it's okay to say, safe here at the Maths Learning Centre. This is not the Maths Learning Centre, but today it is, because I'm here. Bring the Maths Learning Centre with us. Right, cool. Now that was more of an aside, like it wasn't part of my plan. It's only a rough plan anyway. But it's usually a good idea to ask yourself any statement, do you think that they could ask you to prove it? And this is not a very long proof. It straight up uses the definitions of the things that we're doing. So they could ask this. They have asked it before, based on students coming to me and said, they asked me to prove this. If when you come after your exam and after you've dealt with the feelings, you can come back to the Maths Learning Centre and tell me all about it, and then I'll know, so I can pass it on to next year's students. Especially the summer school students, they're in a certain amount of distress. So. Okay. So in the chat, someone has said, well, how do you show that something's a basis in the first place? Like, how do you show that they span? I may possibly defer that to a different revision seminar that already exists. There's plenty of them on that, on the Maths 1B and Maths 1A resources page. But the idea is, though, that to show that something spans, what that means is that every vector in the subspace you're thinking about has to be a linear combination of the vectors that you want to be a basis. So, these are the same statement, V1 up to VK span W, or W is the span of V1 up to VK, it's the same thing. So the first thing to check is that, well, if the vectors are going to span W, they actually have to be in W. If those vectors aren't actually in the subspace W, they're never going to span W, they'll span something else. So sort of rule 0, secret rule 0 is that W1, all of the vectors they have to be in W. That's the first thing to think. Like if someone just said, these vectors, do they span this subspace? The first thing I would do is check if they're in the subspace itself. And if they're not, then whatever. And every subspace has a rule for how to decide if things are in it. So that's secret rule 0. And then there have to be enough of them to span W. So if you know the dimension of W, if you go, oh, that's a plane, then you're going to have at least 2 vectors to span it. So these aren't proofs, these are just ways to decide. Yep?
Would you need at least 2 vectors to span a plane, or exactly 2
Well, you can span a plane with 15 vectors, you just don't need 15. Yeah. So that's why you need the linearly independent rule. So you're right, you do need exactly 2 vectors to span a plane, but you can do it with more, you just don't need more. And that's why the basis rule has a linearly independent thing that forces you to have the exact smallest possible number. All right. So then to actually tell if they span, the only way to do it, just wait, one last thing, is that you're going to have to do this. You know, suppose W is in big W, and then find the coefficients that go with the vectors to show that W is a linear combination of them. And that's I don't have any more advice than that. You have to find the correct coefficients that make this a linear combination of that. And you have to do it in general using algebra because it has to work for all possible W's. Yeah. So you have to use algebra, you can't just pick a vector and show that it's a linear combination like 117 or something, because it has to work for all the vectors. That's the key thing. That's what span is. Everything in W has to be a combination of those things. Yeah. If there is even one vector that is not a combination of those, then they don't span it. Yeah. That's span. So the quickest way to find a basis is to have one already. But the quickest way to find a basis is to find all of the points in the subspace. The point of a basis is to find all of the vectors in the subspace. So the first thing you need to do is to find all the vectors in the subspace if you want a basis. So just as an example, no, I'll do that example later. I'll come back to that. All right. Someone has asked in the chat, can you use, just as an aside, going back to this proof, can I use statement abbreviations like if and for all and there exists in a proof? And the answer is yes, no, no. Unless these are inside set notation, and then that's okay. But if you want to say as part of an ordinary sentence for all x, then you use the words for all. Do not use these symbols. They are specifically reserved for set notation and probability notation. Do not use them in a proof. This is okay. That's just an abbreviation. These are symbols. Yeah, that's my advice. It makes me very upset when people use this in the middle of a formal proof. Sorry. So that's that question. So if IFF is pretty much the only one that's okay, which is short for if and only if, by the way. Okay. So where was I? Orthonormal bases. So the point is, here we go. If you want an orthogonal basis or an orthonormal basis, first you need a basis. That's the first thing you need. So you can't get an orthogonal or an orthonormal basis without getting a basis first. If you are very lucky, then the basis you think of will already be orthogonal or orthonormal and life will be good. But if it is not already orthogonal or orthonormal, you will have to turn it into one that is. So to find I'm just going to say how to find an orthonormal basis. So to find an orthonormal basis, step 0 is to have a basis. Whatever way you have to find that basis is your call. You can either be given it to begin with and say, here is a basis, find an orthonormal basis. Or you can not have a basis yet and you'll have to find the basis yourself. And then step 1 is do the Gram-Schmidt process. And I'm sorry, it's the only way. There is only one way to find an orthonormal basis in fairyland, and it is to do the Gram-Schmidt process. I'm sorry. Sorry. Except there is one exception to that. If your basis is already an orthogonal basis, then you can just divide them all by their lengths. Unless... if they're already orthogonal, then just divide them all by their lengths and that'll make it orthonormal. But it is very rare to already have an orthogonal basis. But I will say, if you didn't notice they were already orthogonal, it would turn up in the Gram-Schmidt process anyway and it'd be okay. So, yeah. How do people feel about the Gram-Schmidt process? We've got some mixed feelings. I have strongly mixed feelings about the Gram-Schmidt process. I'm sorry, it's the only way. And I will say that in the exam, they recognise that you only have a certain amount of time. They will not ask you to do a Gram-Schmidt process on more than 2 vectors at once. So my experience of the last 15 years is that no, they have never asked that. Now, just like the ads for superannuation, past performance is not indicative of future performance. So take that, recognise that, but they've never asked that because they just don't have time. And they also just don't care that much. The main thing they want you to be able to use the Gram-Schmidt process for is orthogonally diagonalizing a matrix. Because you have to use it during that process. Yeah, so there you go. But I will just say, the Gram-Schmidt process has a cycle of 3 steps. Your lecturer calls it 2 steps, but I always get it wrong if I try and do it in 2 steps and lose or gain minus signs along the way, so I do it in 3 steps. And because I haven't done it for a while, I shall sing the song. We use the Gram-Schmidt process because we need to find an orthonormal basis, and to start we normalize, project, subtract, normalize, project, subtract, normalize, project, subtract, normalize time. Thank you. To the tune of Fairyland Clickety Clock from the TV show The Fairies, written by Jen Watts, used by permission. Okay. I really was. I asked her. She was very confused. But, you know, gracious enough to let me do it. Okay, so that's the steps. Project, subtract, normalize. So the process of projection is this. So projection, oh, for the sake of Frel. I really only chose to do this because I wanted to sing the song. Also, a lot of people were confused about this semester, as I recall. So, when you project one vector onto other vectors or onto a subspace, to project a vector onto a set of other vectors, technically the span of those vectors, you get the projection, oh damn it, I'm just going to say, technically it's the span of those vectors. So the projection of U is, okay, so here's the thing. I'm not going to write it down straight up. It is going to be there. I just want to move it down. The projection of U, so U is a vector. It is wherever the vector is. And we're going to find a new vector that is as close as possible to this one, but still in that subspace. That's what projection is. So just in what we're thinking is, but in the subspace. That's what projection is. So, if it's in the subspace, then it has to be a linear combination of these vectors, because that's what span means. And so it's going to have to be something times V1, I need more space than that, something times V1 plus something times V2 plus something times Vk, and however many vectors there are. If it's going to be in this subspace, it has to be a combination of those vectors. And the correct thing to put in this spot is the vector I'm doing this action to dot with the vector I want it to be next to. So this will be U dot V1. And this will be U dot V2. And this will be U dot Vk. That is the action of projecting. Problem only works if the V1 up to Vk are orthonormal. Which seems like circular reasoning, right? The action of the Gram-Schmidt process, which finds an orthonormal basis, has a piece which is called projection, which requires you to have an orthonormal basis to do it. Crap. But that's okay, because we do it one vector at a time. If you've only got one vector, then to make it orthonormal, you just have to divide it by its length. And now you've got a second vector you can project onto the first one. And now you've got two vectors that are orthonormal, and you can project the third one onto those two. And now you've got three vectors that are orthonormal, you can project the fourth one onto those three, and so on. So that's the plan. Find an orthonormal basis for the subspace W, which is the set of vectors x, y, z, t in R4 such that x minus y plus 2t is 0. That's the thing I'm going to do. So this really is a subspace. I know it's a subspace because it's defined by a homogeneous linear equation, and any set in R whatever defined by a homogeneous linear equation is always a subspace. So it is definitely a subspace. But I can't find an orthonormal basis for this subspace until I have a basis, so I'm going to have to find a basis. And the only way to find a basis is to first know what all the vectors in the subspace are, which is a problem because this subspace is not described in a way that tells me what its vectors are. All it says to me is how to decide if a vector is in this subspace. If I had a random vector and I wanted to know if it was in this subspace, I would sub it into this equation, and if it came out to 0, it would be in the subspace. And if it didn't come out to 0, it would not be in the subspace. So this doesn't tell me what the subspace is, what the vectors are. What I'm going to have to do is solve this equation to find all of the vectors in this subspace. Like that. So this is one equation in 4 unknowns. It looks like 3, but there's supposed to be a z. It just doesn't appear in my equation. And so Traditionally, if you had a set of equations and a set of number of unknowns, you'd make a matrix and you'd row reduce and you'd put in free variables. My matrix is only going to have one row because it's only got one equation. So it's probably quicker for me to just do this. Like that. And so that means that the vector x, y, z, t, which is in W, is going to be y minus 2t, y, z, t. I could do free variables if I want, but I just decide not to today because I can't be bothered making a matrix if there's only one row. Nothing up my sleeves. This coordinate has a y in it, this one has a y in it, these two don't, so I have y, y, z, t, and minus 2t, 0, 0, t, and 0, 0, z, 0. And that is y times, oh, don't want a t, yes, y, 0, 0. Damn it, what am I doing, David? These are all the y's, these are all the t's, these are all the z's. I have y lots of 1, 1, 0, 0, and t lots of minus 2, 0, 0, 1, and z lots of 0, 0, 1, 0. And look, it's a linear combination of three vectors. A span, if you will. And that means that these three are a basis for my subspace. Oh no, sorry. Without the curly brackets, it's is. Without the curly brackets, it's are a basis, and with the curly brackets, it is a basis. Because with the curly brackets, it's one thing, and so it's singular. And now that I have a basis, I can find an orthonormal basis. But before I decide what to do my Graham-Schmidt process, I should put them in a better order than this. So first, I just want to check something. If these were all orthogonal, then I could just divide them by their lengths. So this one dot this one is minus 2, so they're not orthogonal. This one dot this one is 0, so they're orthogonal. This one dot this one is 0, they're orthogonal. Ah, they're nearly orthogonal. It's just these two that are a problem. That's so annoying. Damn it, can't just divide them by their lengths. Sorry, everyone. But I will start with these two because they're already orthogonal. I'm going to start with this is going to be vector number 1, this is going to be vector number 2, this is going to be vector number 3. Actually, no, I'm going to make this one vector number 2 because it's only got 1s in it. That looks easier to me. Yep, let's do that. Okay, yes. The Graham-Schmidt process. So we start by normalizing the first vector. In your course, can I just check something, if you have memories of this? When people do the Graham-Schmidt process, do they traditionally call the beginning vectors u and the ending vectors v, or the other way around? Okay, that's sad. I like to finish with u because they're unit vectors at the end. But I get the point of uv, it's in alphabetical order, that makes sense, u before v, but you know, you get to choose. I'll do what the lecturer did. So u1 is going to be this vector, and the length of u1 is 1, because 0 squared plus 0 squared plus 1 squared plus, you know, just to be complete. And so I divide by 1, and I get nothing happens, and so this really is my first vector. So we're good. So I've done the normalized step, which is the only one necessary for just one vector. And then what I'll do is I'll project the second vector onto the first one. So u2 is 1, 1, 0, 0. And the projection of u2 onto the other vector we've got so far is going to be a multiple of v1. And the correct thing to go in this spot is the dot product of this with v1. And this dot product is 0, so I just get the 0 vector as my projection. So this is what happens if they're already orthogonal. And so that was the projection, and now I subtract. So this is the u2, this is the v2 dash that they mentioned in the lectures. And so that'll be this minus that, which is still the same. And then I normalize. The length of this thing is the square root of 2. And so therefore v2 is 1 on root 2 times this thing. I choose not to put that 1 on root 2 inside the vector. That's a waste of time. If you have to enter it into Mobius, then I'm sorry, you have to put the one on root 2 inside the vector, but we're not in Mobius. You horrible machine. So we will not do that. So now I have two vectors. And the two vectors I've got, this vector and this vector, are now orthonormal together, which means that I can project onto the two of them because they're orthonormal, and I can do the projection process. And so here we are. So project. So u3 was this vector, and the projection of u3 is this vector, so I'm going to have minus 2, 0, 0, 1 dot with the first vector I made times the first vector I made plus minus 2, 0, 0, 1 dot with the second vector I made times the second vector I made. And that is the projection. And so that dot product is 0. I'm right, I made 0, 0, 0, 0. That dot product is 0, so I get 0, 0, 0, 0 for that one. This dot product, the root 2 can come out of it, because that's how dot products work, and I'll get minus 2 plus 0 plus 0 plus 0, so I get minus 2. And 1 on root 2 times 1 on root 2 is 2. So 1 on 2. And so I get this. This time you should bring the coefficients in because I'm about to subtract. So v3 dashed is the vector I used to have minus the vector I just made. So I've done the projection, now I have to do the subtraction. So minus 2 minus minus 1 is minus 1, 0 minus minus 1 is 1, 0 minus 0 is 0, 1 minus 0 is 1. This is my vector. And now I normalize. So I need the length of v3 in order to normalize, which will be root 3. Just going to skip that bit of working.
What is your class, man?
And so therefore my third vector is 1 on root 3 minus 1, 1, 0, 1. Now, if someone was reading your Graham-Smith process, it may be difficult for them to figure out what the actual final vectors were because they're all mixed in with your working, and so you're supposed to summarize it at the end and say the orthonormal basis is my first vector was 0, 0, 1, 0. My second vector was 1 on root 2, 1, 1, 0, 0. And my third vector was 1 on root 3 minus 1, 1, 0, 1. Ta-da! Orthonormal basis. Let's just check if it really is. The dot product of those two is 0. The dot product of those two is 0. The dot product of those two is 0 because now I've got a minus 1 and a 1 together. That's nice. Minus 1 times 1 plus 1 times 1 is 0. Yep, and they all are length 1 because I did that normalizing. So they really are an orthonormal basis. It was worth checking. If one of them didn't come out to be the dot product correct, I would have gone, oh no, I've done something wrong earlier. So it really is an orthonormal basis for that subspace. Why do I care? Well, A, because people keep asking me to do it in order to assess whether I can pass this course. Well, not me personally. Maths 1B is much more enjoyable for me because I don't have to do an exam. But the other reason is the point of an orthonormal basis is that a basis allows you to set up coordinate axes inside your subspace to locate everything. And vectors that are orthogonal, your coordinate axes are actually at right angles like you expect them to be. And vectors that are length 1, all the marks on where the numbers are on the axes are the same distance apart. If it's not orthonormal, then one of them, the one on this axis here might not be the same distance as the one on this axis, and that's annoying. And so that's what an orthonormal basis is for setting up coordinate axes. Cool. So I don't know a way of finding an orthogonal basis as opposed to an orthonormal basis, but that's okay because an orthonormal basis is also orthogonal. So quickest way to find an orthogonal basis if you haven't already got one is to find an orthonormal basis. Yeah. Technically, if all I wanted was an orthogonal basis, I wouldn't have to do that final normalized step because I don't care about the last one being normalized. But I do have to normalize the other ones along the way or the projection step won't work. So, yeah. I'm going to stop talking for 30 seconds.
I was singing this as well today.
Stopping, normalize, project, subtract, normalize, project, subtract, normalize, project, subtract, normalize, time. Thank you.
Right, so at this point, it would be useful.
I would.
This one I would like to know if someone has a question about what I've just said. Yep.
Feeling anything?
Yeah, that's all this.
So an orthonormal basis, they're all orthogonal to each other. They're all at right angles and they're length 1. And an orthogonal basis, they don't have to be length 1. They only have to be at right angles.
And then that's a proof.
And so if you want, but an orthonormal basis is a special kind of orthogonal basis. So if you want orthogonal, you can just find orthonormal and it's the same thing. It's just better. It's like someone saying, could you give me chocolate? And you would be happy with anything. And then they give you lint and you go, oh, yay. So, same idea. It must be good because the dude on the ad is like so intensely loving the chocolate so much. Okay.
Some dude, this guy.
Would someone be brave and tell me
just like,
something in what I said, however small, that they had thought, I would like to remember that. This is what I do one-on-one in the Maths Learning Centre, and we're doing it very bravely in a big room. Thank you. I like the song. That's why I said earlier there's only one way to find an orthonormal basis in Fairyland, because the song is from the fairies.
Yeah.
It's because in Fairyland there's only one way to find the time, which is to sing the song. Yeah. My daughters were obsessed with the fairies when they were small. So it's in my head forever. Okay.
Obsessed with the fairies.
I'm going to do a quick thing on L'Hopital's rule.
L'Hopital's rule. The hospital's rule.
And the first thing I'll say is, which is not really relevant to the actual rule, is that it's French. So you don't pronounce the H. because French people
L'hôpital.
don't pronounce H's.
They say hospital.
It's l'hôpital's rule.
No.
Like
And that's why the A
hospital.
is an R, because all A's are R in French. There is no A in French. So it's l'hôpital. And last thing, there's a circumflex accent on the O, which is indicating there's a missing S, because the English word is hospital. And because the S is missing, there's a circumflex accent on the O. L'hôpital. Because French people don't pronounce S's either. And sometimes they leave them in and sometimes they remove them and put a circumflex accent on the O. And sometimes they have some other weird ass spelling thing that they've done. The reason why English spelling is so bad is because of the French. So there you go. Blame the French. It's their fault. And the last thing to say is l'hôpital is not the person who proved this rule. He just paid someone to do it. He wanted a theorem and he paid someone to prove it for him. Yep. Can't remember his name, sorry. But, you know, Google it. I'm sure it's there somewhere. So there you go. It's now like the Marquis de l'Hôpital. Yeah. Anyway, so l'Hôpital's rule. So l'Hôpital's rule is a way of finding limits.
Oh. Nah, dude. And then Philip in the chat, when doing
That's what it
proofs
is.
exams, can we
That's
use
what it's for.
documentation such
So if
as
anyone says
OP?
l'Hôpital's rule, you know you're finding limits.
And he was like, you can use this one, but you can't use this.
And
This is for probability and stuff. But I'm like, what's up?
so let's just step back a bit. Limits have all these rules. If there's two pieces or two functions, two separate pieces, and you know the limits of both of them, if you combine them in any way you like, you can usually just combine the limits. So if you know the limit of this is 4 and the limit of this is 3, then when you add them together, the limit of the sum will be 7. And when you divide them, the limit will be 3/4. But the problem happens if one of these doesn't have a limit, then usually when you add them together, the limit doesn't exist. But if they both don't exist, if you add them, you can still end up with the limit existing. And so all of your limit laws only work if all the limits exist that are involved. And there is one even worse problem. Or maybe it is Bernoulli. Sorry, someone said I think it might have been Bernoulli. But there were several Bernoullis. I don't know which one it was, but you know. So there is one really important limit law, which is the only limit law which will tell you whether a limit exists or not. The limit law for division says, this is just leading up, we're not even at L'Hôpital's rule yet. The limit law for division says that if the limit as x approaches a of f of x is a, now let's do it as capital F so I know which one goes with which one, is f, and the limit as x approaches a of g of x is capital G, and they both exist, then the limit as x approaches a of f of x divided by g of x will be different things depending on what f and g are. So it'll be just straight up f divided by g. You'll just sub it in and go, yep, this is the answer when g is not 0. So if the denominator is not 0, sub it in and it's fine. Does not exist when f isn't 0 but g is. So if the top isn't 0 but the bottom is 0, the limit doesn't exist. And it will be some flavour of infinity. It might be plus infinity, it might be minus infinity, it might be trying simultaneously to be both plus infinity and minus infinity, which is a very bad kind of not existing, but it just won't exist. It won't be a number. So DNE, I won't rub it out. not a number. So if you do computer science, not a number is actually one of the answers that a calculation can give, and it's this sort of thing. And who knows when they're both 0? Like, the limit law for division does not tell you what the answer is when they're both top and bottom are both 0. L'Hopital's rule is specifically designed to deal with this situation. So if the numerator and the denominator, when you do the limits separately, the numerator exists and the bottom and the denominator is 0, not 0, just sub it in. If the numerator and the denominator, the top isn't 0 and the bottom is, limit doesn't exist. But if they're both 0, this limit law does not tell you what to do. And when you first learn limits, you factorize them and cancel something out. Or you divide everything by x squared or something, and you keep going until you get to something that you do know what the answer is. You make it not 0 over 0. And L'Hopital's rule is designed to deal with this situation. So your two pieces of advice are: one, make it not 0 over 0 anymore, or two, to do L'Hopital's rule. So the reason I say this is that it's really, really, really important to know that this is the situation that goes with L'Hopital's rule. Now, L'Hopital's rule is a little bit better than that because it will work even in slightly different situations than this. But if you don't get 0 over 0, you can't use L'Hopital's rule, and you shouldn't have tried anyway because there should have been another way. You should have just subbed it in. No point using L'Hopital's rule if you can just sub the numbers in. It's a waste of everybody's time. So L'Hopital's rule goes like this. So if the limit as x approaches a of f of x is 0, and the limit as x approaches a of g of x is also 0, or the limit of f of x is sort of equal to infinity, and the limit as g of x is also equal to infinity. Not that limits can be equal to infinity, but whatevs. That's why I put in inverted commas. Because infinity is not a number, and a limit is explicitly defined to be a number, and so whatevs. Just leave it at that. Probably David Roberts, who's one of my staff, would come in and say, "But David," and I would say, "Shut up." No. Okay, so it also works if both the top and bottom are both infinity. And they don't have to be the same infinity either. It doesn't really matter. So if this happens, then the limit as x approaches a, and this a can be infinity. I'm sorry, you're allowed to put infinity in that spot because you don't have to have a number there. Of f of x divided by g of x is the same answer as the limit as x approaches a of the derivative of f divided by the derivative of g. That's L'Hopital's rule. And we have to be extremely careful when we talk about L'Hopital's rule, because this, without the limits, is emphatically almost never true. F of x divided by g of x is very much and completely not the same thing as f dashed x divided by g dashed x. It's just that they have the same limit at this specific spot. They are not the same, they just have the same limit here. And the only places they have the same limit, I mean, it's not impossible for them to have the same limit elsewhere, but the only places they're guaranteed to have the same limit are places where both f and g are 0. That's L'Hopital's rule. So it's a really cool rule. It's top notch, but it only works sometimes. But that's nice, because the only times it works are the times we need it to work, because they're the only times we were having trouble before. So really nice, right? Here's a limit. The limit as x goes to infinity of x cubed plus 2x plus 1 on e to the power of x. All right, as x goes to infinity, this is infinity. As x goes to infinity, this is also infinity. And what we mean by that is when x gets very large, both of these get also very large. So the limit as x cubed plus 2x plus 1 as x goes to infinity is infinity, and the limit as x goes to infinity of e to the x is infinity. And so we're allowed to use L'Hopital's rule, and therefore the limit as x goes to infinity of x cubed plus 2x plus 1 over e to the x is the limit as x goes to infinity of 3x plus 2, cx squared plus 2 over e to the x, and it's still infinity over infinity. Do you know what? I'm going to call this limit L, and then I don't have to keep writing it. So if you really want to use L'Hopital's rule formally, you have to do the bit where you do the limit of the top and bottom separately to convince the person reading it and yourself that you're really allowed to use it. So the limit as x goes to infinity of 3x squared plus 2 is infinity, and the limit as x approaches infinity of e to the x is also infinity. So use L'Hopital's rule. And therefore L is now the derivative of this divided by the derivative of this. The limit as x approaches infinity of 6x over e to the x. Crap ass, it's still infinity over infinity, so I do it again. And so therefore use L'Hopital's. And so therefore L is 6 on e to the x. And now the limit of the top is 6 because it's the number 6, and the limit of the bottom is infinity, and number divided by infinity is 0. Ta-da! The only limit you know when x goes to infinity is number that isn't infinity divided by infinity, which is 0. So that's a full L'Hopital's rule solution for x going to infinity. Sometimes people don't care that much and they'll just say, they'll skip this sort of bit and they'll say use L'Hopital's rule at each step. And they'll just do equals, 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 equals. But officially you're supposed to explicitly say what the limit of the top and bottom is every time. So, yep.
But do we need that for exams?
No idea if we need it for exams or not. So what I would do is leave some space, and if you have time, go back and fill it in. Yeah. Yeah. So when they taught L'Hopital's rule in this course, I'm pretty sure, at least in the lecture notes, I don't know what happened in the videos, they spent a decent amount of time turning things into something you can use L'Hopital's rule for. And I just want to mention just a couple of those. Nope. No, I don't want to do that. So apparently in the practice questions, their solutions just have, instead of all of this, it just says that sort of thing. Which is short for, I declare that this limit is infinity over infinity. Right. So this is the long version and that's the short version. So if they do it in their practice questions, it's probably okay for them for you to do that in the exam. I only say probably because I don't know. Whoa. Just give me a second. That one. What's the limit as x goes to 0? Let's say x goes to 0 from above, of x to the power of 1 over x. This is not even a fraction, but all of our limit laws, like basically all of our decisions about limits are almost always about turning things into fractions. So if this limit really does exist, then if I did ln of it, the answer would be ln of whatever this limit is. And so I'm going to do the limit of ln of this and then do e to the power of that to cancel it out. Even better, that. Because e to the power of ln of anything is just the thing. They're designed to cancel each other out. And the limit law for composition of functions says that this, if the limit exists, then this will be true. We can bring a limit in and out of a continuous function. Okay, because e to the x is continuous. Okay, so I'm just going to find this limit now. Well, ln does the thing that exponents come down. And now it's a fraction. Oh crap, the top's infinity, the top's minus infinity and the bottom's 0. Which isn't any of our things. I really thought I had a good plan here. Maybe this limit doesn't exist. That'd be sad. I can't use L'Hopital's rule if the top and bottom aren't the same. I hate it when this happens. Anyone got an idea? Or has seen this problem before? Sometimes I'm acting when I do this and sometimes I'm not. I'm not acting today. Or am. It would seem to me that minus infinity divided by 0 should be infinity, right? Because straight ordinary number divided by 0 is infinity. And so minus infinity divided by 0 should be even more infinity. Oh, I feel like I'm going to get annoyed at myself now.
From the beginning, you make it x to the power of 1 over the square root of x.
To the square root. Still going to have the same problem, isn't it? Because we'll get a root x here.
Oh, yeah.
Someone suggested putting x ln x on the top. But do you know what the limit is? Yeah, someone said, is 0 times infinity 0? And the answer is, could be infinity, could be 7. That's the confusion and horror of limits for you. No. Yeah, someone suggested that. To get that. Problem is, x ln x, I don't know what that limit is. Oh, just a minute. That one I can do. That I can do. Yes! That's the answer. I feel good now. Now the top is minus infinity and the bottom is infinity. And it's okay, I've got infinity over infinity. I can use L'Hopital's rule. The derivative of the top is 1 on x. The derivative of the bottom is minus 1 on x squared. And so that works out to, and I'm going to go to the next page because I'm not going to squeeze that in. So that was from L'Hopital's rule. So now if I multiply this and this by x squared, I'll get x on 1 minus x on 1. If I multiply that by x squared, I'll get x. Multiply that by x squared, I'll get... and that limit is 0. Okay. The limit of x times ln x is 0. And so this one is 0 over 0. So I could do L'Hopital's rule back there and figure out what this limit is. I have the feeling it's going to cause the same problem though. We're just going to get back to something with an ln x over x in it again. Just watch this. If I differentiate that, I'll have to use the product rule, and that is 1, the derivative, and we keep the ln x, and then we'll keep the x and differentiate the ln x, and we'll get ln x minus 1. And the derivative of the bottom is 2x, and so we're going to get ln x minus 1 over x, which is again minus infinity over x, over 0, and we haven't solved our problem. I actually don't know what to do. I'm very sorry. I think the answer is infinity. But I don't know. Sorry. Give me a second. If the limit did exist, wait. It doesn't exist. It doesn't exist. Sorry, this isn't a L'Hopital's rule thing, but I'm so excited. No, I thought I had it, but I don't. Sorry. Doesn't matter. I really thought this would be fun, but if this limit exists, But no, not going to do it. Sorry, don't know. And if you're in an exam, you'd go, don't know. You will have proved that you know lots of things about limits, and that will get you almost all the marks. And so you'll just move on. And if it makes the difference between passing and failing, they'll go in here and say, they proved they knew lots of things. I'll give them half a mark and now they pass. Like, that's what they do. If you are at 49.5 out of 100, they'll go and find a mark for you. They're like that. They're trying their best to give you marks in exams, which is not your experience of the written assignments, right? Because a lot of the tutors who mark the written assignments would like, you did this trivial thing that I think I don't like. I'm going to not give you the whole marks. That's so that you learn things. But yeah, I'm not sure I agree with it, but that's the way it is. But in exams, they're really trying. They really don't want anyone to fail. If x was going to infinity, maybe. If x was going to infinity, we would have gotten to here, and then it would have been infinity over infinity, and we could have used L'Hopital's rule as it was, and that would have been okay. We'd get a 1 over x divided by minus 1 over x squared, which we've already dealt with before. Oh, sorry, 1 over x divided by 1, and then the limit would be 0. Well, that's surprising. Just a second. Huh. So the limit of ln x divided by x is, you'll use L'Hopital's rule because it's infinity over infinity. See, I'm so used to not pronouncing the h that I usually don't write it. So it's L'Hopital's rule on infinity over infinity, and now this is not infinity over infinity anymore. The x goes to infinity, 1 over infinity is 0. Oh, okay, and so that would mean that the limit as x goes to infinity of x to the 1 on x is e to the power of the limit as x goes to infinity of ln x over x, which is e to the 0, which is 1. Cool. The infinitieth root of infinity is 1. There you go. Let me just check if my working was right. Yeah, here. Okay, so we couldn't figure it out as x goes to 0, but we did figure it out as x went to infinity. So there you go. Sorry for making up something. Well, I'm not going to apologise. Sometimes you make up something and it doesn't work. This is why it takes them months to write the exam. You right? It's not just some dude sitting in a room trying to come up with questions. They check against each other and check to see if it actually works. And if it turned out that something slipped through and there was a question in the exam that was impossible, they would cut it and either give everyone the marks for it or remove it from the mark scheme. So just bear with it. I do have a story from when I was a school teacher. My head of the maths department in the school I was at said that when she was in 3rd year, she did a course and no one knew how to do any of the questions because the lecturer had put actually unsolved problems on it. And so, she just underlined all the words and wrote everything she knew about all the words that were in the questions, and they gave her full marks. And fired the lecturer. So, anyway, that's an extreme case. But it's never a bad thing if you don't know what to do to just say what you know about L'Hopital's rule, right? I mean, if it's about L'Hopital's rule, you don't do a Graham-Smith problem and say what you know about L'Hopital's rule. That's probably not worth the problem. Okay, where are we up to? What time is it? Okay, when am I supposed to finish? 11? Okay. What kind of thing for differential equations would you like, whispering person? There's several things on the board. I choose not to talk about the mechanical vibrations, I'm sorry. That's a specific application, and if they want you to talk about that in your exam, they will repeat the whole spiel about what it means. They won't expect you to remember the formulas that go with it. In my experience, since they changed the curriculum in 2018, they haven't expected you to just remember things about specific applications. They've started from scratch as if you've never heard of it before. So the mechanical vibrations were a second order DE thing, as far as I recall. So I could talk about that. I could talk about convergence of series. I'm going to spend 5 minutes on this root 3 thing. Nope, not series, sequences. So they spent a long time in the notes, so like quite a lot of space. I don't know how many minutes or hours of videos they spent. They spent a long time talking about series and a little bit of time talking about sequences. They talked about sequences just before they did Newton's method. It was a weird spot to put Newton's method, I have to say. But anyway, well, that's up to them. So some of the sequences that they talked about, just let me say, a sequence is a list of numbers, and a series is a sum of numbers. That's the difference. So a series is made of a running total of several things, and a sequence is just the numbers themselves as a list. Whereas a series, you add them all up and that's the series. So a sequence is a list of numbers, a series is a sum of numbers, and the short version of this is, the sum of, like that. That's what a series is. But a sequence is just the list of ANs. We're not adding them together, they're just there. So it's really important to know if they've said, does this sequence converge or does this series converge? Because they are different questions. A sequence converging if I have the n that I'm up to and the value of AN here, then A1 might be this, and A2 might be this, and A3 might be this, and A4 might be this, and so on. And a sequence converging is about the dots getting closer and closer to a particular line. This is what a sequence converging looks like. And they really are dots because there's nothing in between 1 and 2. It's not like I have an A1 and a half, there's just an A1 and an A2. So they'll get closer and closer to each other, the successive terms, and they'll get closer and closer to a specific number. And the formal definition, which I don't think they give in this course, is that as close as you want to be to the number they look like they're going to, you can get to a point where everything beyond there is within that distance. So if you want to be within 0.01 of this dotted line, then there will be a point where everything after that is within 0.01 of the dotted line. If you want to be between 0.001, there'll be a later point where everything after that will be within 0.001. And as close as you want to be, you'll be able to go far enough so that everything beyond that is closer than that. That's sequence convergence. Series convergence is similar, except that the thing on the y-axis isn't the value of AN, it's the running total. The official name for the running total is partial sum. I'm going to need two, damn it, I'm just going to put this on the next page. Don't cross it out because I'm going to draw it again. So it may be that your ANs, I'm going to draw them as bars instead of dots, are these. And the running total so we start at the beginning, it's just the same as that one. Oh, colour code, yes, let's do that. And then it becomes this. So you add up everything you've got so far. And then it's this. And then it's this. And if those running totals get closer and closer to something, then that is what the series converges to. And so it may turn out that this running, damn it, that there is a line that these running totals get closer and closer to. And that's the series converging. Yeah. Would someone like to say something about that? Yep.
Every convergence series has its own convergence theory, doesn't it?
Correct. So I'm going to repeat that. If this series converges, which means the running totals converge, the only way that's possible is for these individual sequence to converge to zero. So these have to be going down and down and down so that each time you do a running total, it adds a little bit less to the answer. Yeah. It is actually a thing. If you Google the right things, it's called the divergence test. If you look up your textbook, it's called, the Stewart calculus textbook, it's called the divergence test. In your notes, it's called the necessary condition for convergence. And it's probably a proposition like 8.1 or I don't know what it is, whatever so I don't know what it is, but necessary conditions for series convergence is that this series, if this series converges, then this sequence goes to zero as n goes to infinity. So the only, that's the necessary condition for convergence. And you can see it in this diagram. This gets smaller and therefore this levels off. That's the idea. It is possible for some of these to be negative as well. Like these can go negative, which makes this shorter, but it's the same deal. Okay. So I will say it's much easier to do the contrapositive of this, that's a very fancy mathematical logic word. So if this converges, the only way if this converges, then therefore this has to go to 0, which means if this doesn't go to 0, this doesn't converge. Or if an does not go to 0 as n goes to infinity, then does not converge. Idea being, if these things approached 1, like they got bigger and bigger and got to 1, then as you did the running total, you just keep adding on something that's nearly 1 infinitely many times, and so the answer is infinity. It doesn't come to a number. But that's the idea. This converging means that this goes to 0, which means if it doesn't go to 0, it can't possibly converge. So in most places online, this is called the divergence test, because the only thing it does is tell you that something diverges. If it does go to 0, you still don't know if it converges or not. If the sequence converges to 0, you still don't know if the series converges to anything. You've got no idea. No idea. You're still going to have to do something else in order to tell. So I ended up talking about series convergence anyway. Okay. Oh, that's actually a separate thing. Good. So, technically, we do have to be able to tell if sequences converge in order to tell if series converge. And sequences are still important. Series are very important. Sequences are series are very important, and sequences are very important. Just not quite as much emphasis on the very. Okay, so if I drew this, all of that is just innate of me saying that I just want to do this problem that someone gave me. So, oh crap. Does that thing even exist? Does this mean anything? That's the first question. And if so, what is it? There's probably a fancier maths way of saying that, but this is what I've got. So this thing with the ... is not a series, because it's not just the sum of things. It's got the square roots in the way. But I can imagine it as the limit of a sequence. I could say a1 is root 3, and a2 is root 3 plus root 3, and a3 is root 3 plus root 3 plus root 3, and do that forever. So an would be the square root of 3 plus an minus 1. So this is what I'm making, a sequence that gets closer and closer to the thing I want. And I've noticed that this thing here is a1, and this thing here was a2. And so that's how to make an, is to use the previous one in that spot under the square root. Okay. So that's how to describe this sequence. So does it even exist would mean that that sequence would have to have a limit. And I don't know how to do that. I do know that this is definitely a strictly increasing sequence. Each one of them is just a little bit bigger than the one before, because we've replaced this thing with something that's a bit bigger. And so the answer's a bit bigger. So it's definitely an increasing sequence. And as long as there was a number that was definitely bigger than this, it would have to converge to something. If something's increasing and it doesn't get past something, it's going to have to stop somewhere. That's a theorem. So I don't know how to do the does it exist, but I do know that if it does exist, I can solve the problem. So we have that, the thing we want, I shall call it x. And then that would be the limit as n goes to infinity of an is the number x I'm thinking of. I should call it a, yeah, that would be better. Yeah. The x just makes me think it's unknown, but it's not. Like it, I mean, I don't know what it is, but it's a real thing. Okay. Ready? Perform the limit as n goes to infinity on both parts of this equation. That's what we're going to do. The limit of this side, oh crap. The limit of this side, this part here, the limit of that is a. And I can bring limits underneath square roots because the square root is a continuous function. Actually, I'm going to do the whole thing properly, just a second. The limit as n goes to infinity of an is the limit as n goes to infinity of the square root of 3 plus an minus 1. And so the limit as n goes to infinity of an is the square root of 3 plus the limit as n goes to infinity of an minus 1. Technically, it's the limit of 3 plus the limit of an minus 1, but the limit of 3 is 3 because it's always 3. And the limit of an as n goes to infinity is capital A. And the limit of an minus 1 as n goes to infinity is also capital A because, well, n minus 1 could just as easily have been n. It doesn't really make a difference to the limit. Infinity minus 1 is still infinity. And now I have an equation to solve to figure out what a is. And so a squared is 3 plus a. And so I've got that a squared minus a minus 3 is 0. Because that's tradition for quadratic equations, to put them all on the left-hand side. I could attempt to think of two things that add to give minus 1 and multiply to give minus 3, but it doesn't seem likely. So I'm going to just use the quadratic formula. So a is, so minus b plus or minus b squared minus 4 times a times c over 2a. Where the a I'm talking about is the thing that's traditionally in these spots for the quadratic formula. 1 plus 12 was 1 plus or minus the square root of 13 on 2. Cool. It can't be both of those, it can only be one of them. And, well, it's got to be a positive number. Root 13 is more than 1, so 1 minus root 13 would be negative, so it can't be the negative one. So a is definitely positive. Because, look, they're all positive numbers. It's an increasing function, and so therefore a is 1 plus root 13 on 2. Ta-da! They're all like that. So if you do continued fractions, that thing, you would say, you would set it up as a sequence. So you would call this A, and you would say A1 is 1, and A2 is 1 plus 2 over 1, and A3 is 1 plus 2 over 1 plus 2 over 1. So AN is 1 plus 2 over AN minus 1. And then you do the limit as n goes to infinity. And you'll get a equals 1 plus 2 over a. And you rearrange that to figure out what a has to be. And you get a quadratic equation again. This one I can solve, actually. I didn't mean to, but... Two is one of those numbers, by the way. 1 squared, 2 squared is 4, and 2 plus 2 is 4, so 2 is one of these numbers. And the other number is 1, minus 1. But just for completeness' sake. So I know some numbers that add to give minus 1. It would be 0 and minus 1, but they would not give me a minus 2 here. And so a 1 and a minus 2 works. And again, a has to be positive because these are all positive numbers. And so therefore a is 2. Yep. Which is really interesting. I did not expect that at all. Really want to get a calculator and try it. Wow, it really is 2. Okay, cool, I believe it. Desmos says it's 2. So, gosh, I love Desmos. Right, here you go. Sometimes it turns out to not be a whole number. I mean, the first one didn't. It came out to be square root of something. But when you do continued fractions, they can turn out to be other things. All right. I'm going to stop there.